Today we're going to be continuing with trigonometry, but moving away from just looking at triangles to more to do with graphs and transformations of graphs. So we're going to start with a bit of sectors and then some radians, a bit of graphing, and then we did do a bit about transformations when we were completing the square on quadratics, and we're just going to look at cubics and other graphs as well. So the first bit is GCSE, and then all the rest of it today is AS level, really. Well, graphs and transformations fall into GCSE a bit, but it depends at what point, well, depends which bits we do. So, calculating arc lengths, angles and areas of sectors of circles using degrees is at GCSE. So a sector is just a piece of pie, basically. A piece of a pie, I'm not talking about actual pie. So it's a fraction of a circle, and a segment, which I'll talk about in a minute, is when you take a triangle across, it's the bit that's left with the arc. So arc length is this bit along the outside of the circle. So whenever we want to find the area of a sector, we just think of it as a fraction of the whole circle, and we use whatever the angle of the sector is over 360 degrees, and then multiply that fraction by pi r squared, the area of the circle, and that will give us the area of a sector. Now, the reason that I've also written this down from last session, we did the area of a triangle when you don't know the vertical height. So if you've just got the length of two sides and the angle in between them, do you remember the area of that is half times A times B times sine C. Now that's important because if we draw a triangle along here to make a triangle inside our sector, we can then find the area of that, take it away to find the area of the remaining segment. So hopefully that's a little bit familiar from last time, briefly. And this hopefully makes sense if you haven't done it before. The students seem to find that fairly straightforward, that they're given a bit of it. They just often forget that it's over 360 because they forget that it's an angle over the total angle, which is 360 in a circle. You know, they do things like over 100. It's more just a case of not really thinking about what it is. But most of them actually, in fact, the ones that struggle with a lot of other things find this fairly straightforward. So to find the area of the segment, which is the green bit there, involves doing those two bits. So the area of the whole sector is the 100 degrees as a fraction of 360, 100 over 360, multiplied by pi r squared, where r, the radius in this case, is 10. So that's a bit of a calculation there. And it comes out that the area of the whole sector is 87.3 centimetres squared. We want just this segment, which is that bit there. So we need to take away this triangle. The area of this triangle, using the half AB sine C, is a half times 10 times 10 times sine 100. So that's 49.2. So the segment is going to be the 87.3 minus 49.2, actually, really. But anyway, make it roughly 38 centimetres squared. Does that make sense? Have you done this before? Have you done it before?
A long time ago, actually.
No. Yeah, not with you. No.
Have you done it with school at all? Because of course the thing is that this area of the triangle bit is very much at the higher end. So something that's actually fairly simple often doesn't really get done necessarily. They can find the sector but not the segment because they don't know how to find the area of a non-right-angled triangle. But anyway, so you guys can have a go at doing this now. A load of them. Just have a go at doing those. Do you want me to write the area, reminder to the area of the triangle? Of the triangle area is half A B sine C. So you do need a calculator for this bit. And the area of the segment, which is sector, doesn't look much different from the angle, I think, is the angle times pi. Okay, so have a go at doing those now. No, my calculator's going to have battery. And put your hand up for the thing when you've done that.
Sarah, I've done two.
Yeah.
How many do you want us to do? All of them?
No, that's fine. Should we say call it a day? You get it, basically, don't you?
Okay, I've done the first two.
Okay,
Yeah, I've just done them as well.
that's fine. Let's do that. Okay, so let me get my what did you get for the first one, Rob?
I've got the area of the sector as 113.4. The triangle is 7.6, which should give the segment as 105.8.
Did you get the same way?
No, I got the triangle as different to that.
Okay, let me do it. I hadn't done it yet because the calculator is going.
The triangle, what did you do, Rob? Half times
What's that?
10 times 10 times sine of 130.
I see what I've done.
Are you in radians?
Yeah.
So, yeah, I got 38.6.
I've added the two lengths instead of actually timesing them. I've written it down correctly, I've just punched the wrong button into the calculator, that's all.
Yeah. Now that's always a weird one when you see the kids have done that and you're like, how did you get them to do that? But Okay, so I can't find the pi button on the husband's calculator.
So triangle's going to be 38, which means what, we're down about 75 or so?
Yeah, exactly.
Yeah, that's good.
Yeah.
And Wayne, what did you get for the second one?
For the second one, I got the sector as 89.7 centimeters squared, and then the triangle I got 60.3. So what's that? 29.4.
We've also just pressed plus instead of minus. Yeah, in fact, if I press this, ta-da, there we go. So what you got? Yeah, 29.5. They put there. So yeah, good. So yeah,
Yeah, 20. Yeah, all right.
Just taking care of what you're typing in calculator really. Good. Okay, so that was just the sort of GCSE easing you in for today. Now moving on to AS. The notion.
Paracetamol now.
Sorry, you're going to go now. Are
Shall
you?
I take some paracetamol? No, yes, I'll take some paracetamol now, shall I?
Hopefully this won't be too bad. You might even have come across it before, hopefully. We're just going to talk about radians and the relationship between degrees and radians. Radians were, well, the original measure of angles. I have to say that I know absolutely nothing about grads, so that I don't know when that came in. But I know that the Indians, when they first were looking at how they described angles, basically came up with radians, and so they kind of make a bit more sense really. They're based on circular measure. And degrees only came in a couple of hundred years ago when we started circumnavigating the globe and needed to use a different way of describing angles. So the kids aren't a huge fan of radians because it's like having to suddenly think in a different language, which they're already having to do anyway in maths, and yet they've just spent the first, whatever, I don't know, 10 years of their lives that they've been doing angles in degrees. And then we say to them, okay, you're 16 now, I think you can cope with this. We're now going to do this other measure called radians. And they're always struggling to sort of translate between the two. They haven't got to the point where, and they're unlikely generally, unless they do a lot of practice within the 2 years of their AES level, to really get to the point of being really fluent in radians, so that they don't ever have to keep translating in their head what the degrees were. So hopefully by the end of 18 you can remember. So radians. One radian, so this is the definition that was developed by the Indians or whoever it was, the very first people to pick up with this. Probably Babylonians, they're always good at primitive evidence. But anyway, one radian is the size of the angle formed at the centre of the circle when you've got two radii which are the same length as the arc. So what that means is this length, I take that length round the arc, so that is exactly the same length as R. And then when I go back in to there, the angle formed here is 1 radian. So that's how they defined it, which was very useful because, of course, you can wherever you are, you can stand and you can make a circle of whatever radius is most useful to you. And provided that all those radii are the same, that angle that is created would always be 1 radian. Now, as we progress around this circle a bit more, so this is 1 radian. Oh, and you can write it as rad, or we tend to do a little c, which again can be a little tricky because if you write that quickly, you could end up joining it up and it looks like degrees, but you're likely to be able to tell that it's different, well, when you get more accustomed to it. This is one of the problems that kids have. It's in sort of the, does that make sense category when they're looking at their answers. If they've got something that's tiny and they're writing 1 degree, it's more likely that it was actually 1 radian. So if the arc length is extended to 2 lots of r, then the angle that's created is basically double what it was originally, and so it is 2 radians. And equally, if we extend it so that the arc length is 3 times the radius, that original angle is tripled, and so is now 3 radians. Now, as you can see, this is fairly accurate in the way that I've drawn it. As it's progressing around this circle, you can see that we're almost at 180 degrees, not quite. So 3 radians is almost getting towards 180 degrees. In fact, if you know it already or you were to hazard a guess, it looks almost as if it were about 3.14 radians around. So if we make the arc length 3.14 lots of r, so the angle is 3.14 radians, which hopefully you'll recognise is pi. So pi radians is actually equivalent to 180 degrees. So the half the circumference, as it says, is pi radians pi arc. So sorry, the angle is pi radians, and that is the same as 180. And so we use that as our conversion between radians and degrees. So that's kind of the thing that you get the kids to write down, that pi radians equals 180 degrees. They find this a bit weird, especially because they tend to leave off at radians sometimes, and they've just written pi equals 180. And that's like writing, I don't know what the actual rates are, but that's like writing 39 equals 100. And when you're talking about 39 degrees C equals 100 degrees F, or whatever. The units in those cases are very important, and so they are here. Otherwise, it gets a bit complicated. And unfortunately, some of them, once they've learned this, they go around replacing pi's everywhere, like in non-trigonometry things, with 180. So pi here is just a number. We're saying that 3.14 radians is the same as 180 degrees. So if pi radians is 180, if we want to know what 1 radian is in degrees, we need to divide both sides by pi. So whenever I'm getting them to do the conversion, I get them to remember that pi equals 180, and then do whatever they need to each side to get 1, and then multiply up to get whatever they need. So 1 radian is going to be 180 divided by pi, which is about 57.3 degrees. So on our original circle, that first radian angle, 1 radian, it was about 57.3 degrees. There we go. So this is so the angle at the centre is subtended by the arc. That's just terminology, which is a bit helpful in the circle theorem when we use that, subtended. But I think I'm doing circle. Have I done circle theorem? No, I think I'm doing that with you at the ISW. So we'll talk about that a bit more then. So I'll do just the first ones to show you, and then you can do the rest of them. So to write down the equivalent, here we're given the number of radians. So, well, I don't need to do this with you, but because we're saying it's pi over 2, so pi radians is 108 degrees. Oops, that's an 8. So if I wanted pi over 2, obviously I've just halved that side, so I need to halve that side. So pi over 2 is simply 90 degrees. So you just need to do the same to work out those. And equally, you can write these in radians, and we tend to leave them, as it says, as a fraction of pi. We don't divide by the 3.14. We leave radians so that they look like these ones in terms of pi. So your 60, obviously we can see that 60 is a third of that. So it means it will just simply be a third of that. With the kids, I do sometimes have to say to them, okay, what you need to do is divide both sides by 180 and then multiply by the angle you need. Not when it's easy to see, but sometimes obviously if they were asked for 52 degrees, they'd have to do this and then do some cancelling between these two. Which is obviously still fine. Cancelling like this, not something that's particularly great at for some reason. Anyway, so have a go at doing all these, converting these ones to degrees and these ones on the bottom to radians, please. Does that make sense, what I've explained to you about radians before you have a go?
Yeah, that's okay. It's been a while since I've done them. I took it as second nature when you're drawing a sine and cosine curves. You would always use the pi version rather than degrees. But
well,
yeah, I still have to think about converting them.
Yeah, I mean, at GCSE, because there's no radians, they're expected to be able to draw the sine and cosine graphs and write the degrees on them. And so that's why we kind of start with that and get the kids to do that at AS level and then sort of say to them, and here it is in degree. And they're in radians, and they're supposed to be able to do them both equivalent. But exactly, we do both in AS. By the time we get to A2, more of it is in radians. And you can only do calculus involving trigonometry when it's in radians. So we have to do that in the secondary grade level anyway.
I don't think I've thought of them as radians. Whenever you're doing more advanced calculus, you just do pi. You don't think
matter,
about
does it?
its
No,
radians.
exactly. It doesn't really matter. And I hope, yeah, I think that's the thing really. It's one of those things they need to know about, but actually a lot of the time they're just using it rather than having to really think about what they're doing. Okay, so have a go at it. Wayne, have you seen these before?
Not that I remember whatsoever, but I was just going to ask you, when we converted the, you brought the circumference into it.
Yeah.
There was something there that I didn't quite follow.
Okay.
Obviously circumference is equal to 2 pi r, yeah, and then 180 degrees.
Yeah.
We're kind of changing the right, so it's the length of the arc length.
Yes. But actually, you know how you say circumference is 2 pi r? That comes from this rather than the other way around, because what I
Right,
was
okay.
what I was saying is that when we've got 180 degrees, so that's half the circumference, isn't it?
Yeah.
That happens to be pi radians, which means that this length round here, because it's always the same as the arc length. Ooh dear. Well, so that means
Oh, it's pi
that,
radians. Yeah, it's not
yeah.
giant pi. I'm looking at it and looking at it as if it's pi times radius, but it's not. Is it? It's pi times radians.
Oh no,
Is
well,
that
no,
right?
no, round here. You're right. Sorry, that is a length of pi r. You're absolutely right. Sorry, I should put the r there because so here's my radius here.
Yeah.
So one radius took me to about here. If I basically
Yeah.
had a piece of string and I stretched that round to there, and so that going in there would make 1 radian. Basically, if I
Yeah.
stretch this round the arc length so that I had 3.14 lots of the radius,
Yeah.
so the pi times, you're right, times the radius, then that goes halfway round the circumference. This is something that I don't know if it's because of the way that it's defined or if they just discovered, and I think it's a bit of both, that this is what happened when they measured around a circle. It was always 3.14 times the radius. Whenever they made a circle, yeah, it will be that widget. Whenever they made a circle and they went 3.14 times round with the radius, they discovered that it gave them half the circle. And so that's why they defined the angle then to be that length around the outside. That was just how they defined it, and that's what radians are. Now, then when they came up with how do you find the circumference of a circle, they went, okay, well, when we get to there, it's pi times r. So if we go round again, we've got 2 lots of pi r. And that's where the formula for the circumference of a circle comes from this invention.
Yeah. I think I've just in my own head it's obviously 2 pi r radius, and just converting that to radians
So the
because
angle,
it's not the same thing, is it?
no, so the, no,
No.
no, so that's
I think
2,
that's where.
yeah, so if you just think of let's say that pi is in fact 3, pretend, then basically what we're saying is
Yeah.
if we took the length of our radius and roughly laid it out 6 times, it would make our circle, if we put it round in a loop. That's just
Yeah.
that's how big a circle would be with that radius. That's always the way. So, in fact, this answers this bit of the question. If pi takes us halfway around the circle, so 180 degrees, 2 lots of pi takes us around the whole circle, and then that will be 360 degrees.
Yeah.
So yes, one is the arc length. So when it's got an R, it's going round the outside of the arc length. Otherwise, it is just like this. It's just the angle in radians. So like that.
Okay. So.
Okay. This is something that people find really tricky, and actually for a lot of people never makes sense. I think they sort of they muddle through, but they never fully understand it. But it is just kind of an equivalency thing. So have a go at finishing off these, converting them, and then put your hand up when you've done that. Okay, so Robert, what did you get for B?
Second one I've got pi over 3 equals 60 degrees.
Yeah. And then I already said that one's 360. So we've got 90, 60, 360, and Wayne, what's pi over 6?
30.
Yeah, good. And then going back the other way, oh well, in fact, going back the other way, actually, obviously, that's fairly straightforward. So 60 is pi over 3. 45, Robert, what was 45?
Pi over 4.
Yeah, pi over 4. Wayne, 120.
Put 2/3. Yeah, 2/3 pi.
Yeah, good, yeah. And then 30 again is pi over 6. Good, excellent. So that's just sort of the starting point of radians. And I was just thinking more about what you were saying, Wayne. Obviously, the reason that it's confusing is because it is actually defined so that the amount of it of r that you've got, so 2 pi times the radius, is always the same as the angle. So that's why you're confused between them, because they are sort of the same in terms of size. And yes, you get used to these so that when you look at them, you know that that's immediately, you know that's 90, you know that's 360, 30, 60, so that you don't have to constantly do the conversion, you can just write it down. Now, going back to sectors, kind of makes them a little bit simpler. There are certain formulae that directly can be used. What we do is this is when you've got any angle here, but it's in radians, then we call the arc length L. Going back to how we did this before, whatever fraction of the total, whatever fraction theta is of the total angle, so the total angle is 2 pi. So here, instead of doing our angle over 360, we're doing it all in radians. And then as we said, because that's the same equivalent, it always gives the arc length. As it says, whatever fraction theta is of the total angle, the arc length is the same fraction of the whole circumference. So we just need to do theta over 2 pi would be the same as the arc length over the circumference. So we just need to multiply up by the circumference, which is our 2 pi r. Now, because we've repeated the 2 pi, that's great. We can just cancel the 2 pi, and it gives us a really nice, simple formula for the arc length. The arc length is always just going to be theta times the radius. So, in fact, it's exactly what you were just saying, Wayne. This actually is a formula. I think that we would normally just kind of think of it, we go the other way, like we have here. We start with thinking about the angle and then get to the arc length. But when I was describing it, I suppose I was kind of saying because of the arc length, that's what the angle is, which is true both ways. So, just as we were saying, whatever the angle is times r is that arc length for that angle. That's just it proved, really, using the formula that we already know. Equally, for the area, it's still just the fraction of the area. So you've got the theta over 2 pi multiplied by pi r squared this time. So instead of being able to cancel the 2 pi fully, we can just cancel the pi's, and we're left with the area being half times r squared times the theta. Less obvious than the other one, because the other one, basically, as we said before, the definition of the arc length is that it is the same as the angle, just multiplied by r. So these two formulae, the students are expected to learn off by heart at AS, and if they couldn't, then obviously they could just go back to thinking, okay, it's a fraction of the 2 pi times by the area of the circle. That's absolutely fine. It tends to be one of those things, though, that you know what it's like. If they can't remember the formula, they just skip it. You know, it's like they've completely forgotten how to do it. Or they forget that it's in radians. They use the radians value over 360, and then it just gets really weird numbers. But here we go. So we want to find the arc length, L, and the area, A, of a sector which has a radius of 7 and the angle is 2 radians. So, oh, wow. Okay. Let's draw a circle over here again. Just ignore that one over there. Got caught in the mouse. So here's the radius, 7. 2 is going to be, it should be a bit bigger than that probably. But let's say that's 2, radius is 7. We want this arc length. So because we could do the whole 2 over 2 pi times 2 pi r and end up cancelling them, we end up with just 2 times r, which is simply just saying that's going to be 14. So nice, straightforward. The area just has to be a bit more thought out. You just got to remember there's either half r squared theta, or do the fraction thing. It's easy to just do that. So half r squared theta is just going to be half times 7 squared times 2. So the area of this sector is 49 centimetres squared. And if you were required to find the segment, we'd still just do what we were doing before. We'd find the area of this triangle and then take it away from that. Just got to be careful because that's in radians. Still fine. What is it? Half AB sine C. Half times 7 as A times B is the same. Times sine C, sine of 2. The only thing is, if you put sine of 2 in, and your calculator's in degrees, you're going to get some tiny amount. So you have to make sure that if you're using radians, that you have to convert your calculator to radians. And depends on your calculator how you do that. Mine's in setup, but normally there's some way. What I've done with my other calculator, but you I don't know how on earth I might do it on this one. Look in loads. Oh yeah, so his is in loads and it's currently in degrees. So I can show you that. Not very good. But the third one down is where degrees is highlighted. And on his calculator, I just press the arrow button and then it highlights the radians and I select that on this fashion. Really old-fashioned 20-year-old calculator there on that one. Most of just the regular little Casio ones, it gives you, it's like something like, 112 in terms of like the things that you press. And you get the option of degree, rad, and grad. And the grad apparently is some sort of engineering angle that I've never used before. But there should hopefully be a place where you can change it to radians. If you really couldn't figure out how to change your calculator to radians, that would be slightly problematic. But you could always convert this to radians into degrees and put it into your calculator in degrees, and then that would give you the area of the triangle. But ideally, if there are questions in radians, you just switch it to radians. In the AS paper, they have a mixture of radians and degrees, and the students may need to be able to switch their calculator between during the actual exam. But does that make sense? The arc length and the radius and the area formulae.
Yeah, that's fine, so I'm following that one.
Okay, so then here you go. You can have a go at doing it yourself. Actually, I've written examples which suggest. I'm just going to do this. No, this one is for you. There we go. So for you, find the arc length and the area of the sector. When you've got a circle of radius 5 and the angle is 150. And it says just give your answers exactly in terms of pi. Oh yeah, and what I should say is that's just that's in degrees. These only work in radians. Okay, so Robert, what did you get for the arc length?
The arc length I've got 25 pi over 6.
Yeah. So we had to convert the 150 to 5 pi over 6. And then we'd multiply by the 5, so you have 25 pi over 6. And then weighing the area.
Got 125 over 12 pi. Yeah, 125 pi over 12.
Yeah, good. Yeah, make sure the pi is up there. Yeah, good. Which, you know, the students will all go, oh, it's horrible, that's not a nice number. Because they have like a feeling, a sense of like things that are nice and things that aren't nice. But it's totally correct, so it is nice. Good, yeah, that's it. So it is just a case of making sure that if you are using these, we need to use them for when it's in radians, because the reason that these work is that they take account of it being in radians. Otherwise, you would have to go back to using 150 over 360 times pi r squared, which would be fine. They just have asked for it in terms of pi, so they're generally expecting you to do it in radians. Right. That was just a summary of all of that. Right. Oh look, I did do one. I thought that was an example. Never mind. There you go. 2 more for you to do. Arc length, perimeter, and then arc length and area. 300 range on that. So Wayne, can you tell me what you got for number 1?
Yeah, yeah, I'm starting to struggle with this. I've got the length as 8 centimetres.
Yeah.
And then the area, I've confused myself in terms of, I've done half times 4 squared, but then the angle, you just use 2.
Yeah, you do. Yeah,
I've lost myself.
It is just the 2. I know it's a weird number, isn't it, to have as an angle that big. But it is just 2. So yeah, it's just half times the last squared.
Because I started to think in my head it needs to be in terms of pi for some reason. And
I know, and actually you're right. That is another thing that the students get confused about when we write it, and it's not in terms of pi. But pi is just giving us a number, and it's just making it a bit more accurate. That gives us exact fractions of a circle when it's in terms of pi. But 2 is not an exact fraction of the circle. It is just 2 radians. So you can.
Yeah, exactly. I think that's
Yeah.
I think that's why I started to kind of question it in my head.
Yeah.
So I've got 16 centimetres squared.
Yeah. And what did you get for the perimeter of the sector?
No, I didn't do that bit.
Okay, how would you work out the perimeter?
I think I jumped. Okay. Well, we know all the way around is 2 pi.
Oh no.
So it would be.
All the way. Oh yeah. Okay.
So all the way around is 2 pi.
Yeah.
So it would be 8 pi.
No, the perimeter of the sector is just asking for this bit and this bit and this bit, basically.
Oh, sorry.
Yeah, no, I did it deliberately. Yeah,
sector.
I did it deliberately to catch people out. It's their favourite exam question to catch the kids out. Because you're thinking circumference, really, with perimeter, but actually they really do mean just going around the sector. So yeah, simply the 8 plus the 4 plus the 4.
So it's just 8?
No, so it's 16. So 8 is the length of the...
Oh, sorry.
Okay,
Yes, I'm with you. Sorry, yes. Okay. So all the way round, just out of interest, would it be, the circumference would be 8 pi, would it?
Circumference. No, I've just got to work that out. Hang on. 2 over 2 pi.
Sorry.
Times 2 pi r. 2 times 4. It'll just be 8. No, that's not right. That's a bit open, isn't it?
Because all the way round is 2 pi, isn't it? But we're...
Oh yeah, hang on. You're absolutely right. Yeah. 2 pi r. Oh yeah. I had a complete mental breakdown. Yes.
No, I think that's where I was confusing myself before. Okay.
Yes.
All right, sorry to confuse things.
No, that's fine. 2 pi r is the circumference, so 2 pi times the 4 is 8 pi. You're absolutely right. Yeah. Afraid it's not here. Robert, then number 2.
Yeah, if it's any consolation, Wayne, I stopped reading at perimeter as well, and I did the whole circumference, so I did exactly the same as you did on that last one.
And I think they put it in the exam deliberately as well to get everyone to circumference. You know, that they're just being mean.
Yeah, for the length of that arc, I've got 20 over 3 pi.
Oh. I've got 16.
Because I've got the angle as, what, 5/6 pi?
Yeah.
multiplied by the 8.
I did it as 2/3 pi.
2/3.
Yeah, it's 2/3 pi.
It's my fraction one. Yeah.
Yeah. Yeah, it should be 2/3 pi, and that is
So that'll
what.
be 8/3 then.
16/3.
16/3. Yeah, 16/3 pi, because it's 2/3 times 8.
Yeah.
But yeah, fraction work again. Here we come. This is what the kids obviously struggle with too. And you glance at it quickly and you think, oh yeah, I know 1/20. And so yeah, just be careful. So that's going to obviously have affected your area one as well.
Yeah, I'm just doing a quick recalculation, and hopefully I have now got 64/3 pi.
Yeah. Yep. Good. Excellent. Good. So hopefully by doing that, it has actually dragged up quite a lot of the misconceptions and just general confusion. And will I think we probably have broached everything that the kids find tricky, actually. The fact is that I've told them that it's all about pies, and then there's ones that don't involve pies, and that that can happen when you're solving, say, a trigonometric equation, and you get just these weird answers because they're not a fraction of pi. They can't. It's very difficult to tell what you're expecting. So I guess the key thing is that in a circle, if we're thinking all the time that 1 radian is equivalent to about 57, so 2 radians is about 114, 115 degrees, which looks about right there. So it's just still understanding that whether it's a number or pi, a fraction of pi, it is still radian. Oh, here's the answer.
I think I found what I was doing is I was concentrating so much on getting the radians right, I was ignoring the basic maths of just doing some fractions and multiplication. I was getting that bit wrong because I was trying to concentrate on the radians.
As was I when when I was unable to remember to calculate the circumference of 2 pi r. You get bogged down in the other bit that's tricky, don't you? So you forget the basics. So yes, there are the answers. So that was your introduction to radians, basically, and at AS level, that's kind of all, they do a bit of that, and then they solve trigonometric equations as well, which we're not going to get into really very much. So that's quite involved. However, this is going back to GCSE a little bit, back to graphing. So they've got recognize, sketch and interpret graphs of linear functions, quadratic functions. So that's fine. That's sort of, yeah, everyone does the linear functions. Quadratic functions, you show them and you might go on a bit further. And then these things, you probably show them once or twice and then never again. So they, luck of the draw when they actually remember that it's even in the curriculum. So cubic functions, the reciprocal function, which is 1 over x, exponential functions, and trigonometric functions. So this is all at GCSE. And then they're expected to be able to do translations and reflections of those. Now, often what will be the case is that actually they've just been given 1 over or like 3 over x and asked to plot it. And therefore, it's just the case of them plugging it into their calculator, putting it in a table of values, and then drawing it. And so even if they didn't have any knowledge, hopefully they might be able to figure it out. But the reciprocal one, there'd be some asymptotes that they didn't know about. So they're often given for plotting and not necessarily just sketching, and so they are given clues basically. calculate or estimate gradients of graphs and areas under graphs kind of doesn't come up very much. They are expected to know that if they draw a straight line in the direction of their graph and then work out the gradient of that straight line, that gives an estimate of the gradient of the graph. But whether they remember that is, again, it's one of those things you drop into conversation once and then never again. This is quite a nice matching cards thing that if I was with you we would do, but sadly it can't. But I've uploaded it to the resources, and you can cut them all out and then they match them together so they've got their points to plot and some descriptions of them, and then you get them to label what each of these graphs are. So whether straight line graphs or graph. Anyway, we're going to look at some of these now. So x cubed is a cubic function. When thinking about sketching them, obviously you can put in a couple of points and get an idea for what's happening. But it's just a case of thinking what's happening at the origin first. So if x is 0, y will be 0, so we know it goes through the origin. If we think about x as it goes from being smaller to larger, again, as it gets cubed, that also increases. So as x increases, the y will increase even more so, like that. And the other way, if it's negative, so -1 and we cube it, it's still negative. And so, yes, sorry, just a point about the difference between sketching and plotting is that we don't plot points. When they ask for a sketch, they don't want to see that you've plotted. They want to see a rough, well, I don't mean rough though, in that it looks rough. I mean, they want you to freehand draw it, is I suppose what I'm trying to say. And so as x decreases, y also decreases. So that is what a cubic function looks like. And it's useful to get the kids to draw all of these and to play around with them. And you can use GeoGebra or Autograph or some sort of internet package, graphing package, I mean, to get them used to what these graphs look like and get them to draw sketches in their books so that later they can revise from them, ha, 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 as they do from their books, if only. But just generally getting them used to this. Now, when we were looking at quadratics and we were looking at completing the squares, which hopefully you might remember with this sort of format, what that meant was that we had moved the graph to the right by 3 and up by 2. So it's a translation of the x squared graph by 3, 2. Equally, we can do exactly the same and move the cubed graph to the right by 3 and up by 2 and write it in that form. So there you go. It's useful to think about a point where it's turning, like here at the origin, and think that that's the bit that you're moving, although all the points you're moving, obviously. But it's easiest to take that one and think, okay, that point has moved to the 3 to the right and up 2. So that's where that point will be now. And then it's sort of easier to go, oh, and that bit goes down. Okay, so that's just how we translate cubic, just the same as a quadratic. Here we have another cubic function. It's really tricky to see what is happening with that without knowing a bit more about cubics, which we're going to do next year. Without plotting it. However, this is the sort of graph that if they were given that, it would definitely be a plot one. They wouldn't be expecting them to sketch that at GCSE. Whereas at A level, they would expect them to be able to work out more information, which we'll do next year. So, if we want to translate this function by 3, 2, we think about the bits that we can see. So we can see that this comes at -2, 0, and 1. So all of those bits are going to move exactly the same, 3 along. So the 1 will become 4, the 0 will become 3, the -2 will become 1. And then these ones here are going to go up by 2. So where that's at about 2, it's going to go up to about just above 4. And that one, it's kind of -0.5, isn't it? So I suppose it's going to go up to 1.5. So you just use the information that you've been given about the translation. Look at the key points, the turning points, the origin, and each of the bits where it crosses. And that's where you can figure out how to move it. Now, to make the new equation, and this is really AS level now, what we're doing is whenever we translate it, we're replacing the x value with a new value. Now, in this case, do you remember it's the opposite to what we think? So if it moves in the positive direction by 3, actually the x becomes x minus 3. And when we move it up or down by a number, we just add that number on the end. So we add 2 on. So this is in fact the equation of this graph here. And we could, if we wanted to, multiply it all out and collect it together, but they don't ever expect that. The exam is just time consuming. They just want you to appreciate that the equation changes by putting the opposite number into the x's and putting in the number in the end is the y. And that works, as it says, for all functions. Does this make sense, what I was saying? Any questions about it?
Yeah, it makes sense. It just feels like we're kind of skimming it a bit. So, but as you say, we're doing it next year, are we?
Yes, we are skimming it a bit, and it's just one of those things sort of that at GCSE they wouldn't be expected to be able to do this, but they might be expected to plot this one and then to move it. But also it's quite difficult for us to practice this anyway as we're sort of online. Yeah. Rob, have you done this before?
Yeah, again, quite a while ago. It's sort of coming back, but it does seem to make sense. I am following it, yeah.
Okay, good. So, just going to do the same, but with the graph of 1 over x. Now, I wouldn't you do this because I think I'm going to do this. So, graph of 1 over x is a bit weird because if you think about when x is 0, you can't do 1 over 0. We write that it's infinity. It's basically undefined. So it means that it can never ever touch 0. And then as x gets bigger and bigger and bigger, this fraction actually gets smaller and smaller. So 1 over 2 is much bigger than 1 over 320. And so on. So, and the same is true the other way as it's negative. What that means for the graph is that as the x increases, y actually goes down. So it starts up high and gradually drops down, but actually can never ever touch this bit here. It can never be 0, and it can never touch this bit here because we can't have that 0 either, because there's never 1 over something that equals 0. And 1 over minus, whatever, it looks like this, so it's got rotational symmetry. So this is the graph of y equals 1 over x. So all it's missing is what we call asymptotes, which demonstrate the lines where the graph cannot touch. So they are lines that the graph gets closer and closer and closer to, but can't touch. I think it's over in. Yeah. This is just talking about graphs. Right, there we go. That's what I want. So that is the completed graph of 1 over x. So as I was saying, where they could definitely give this to a GCSE student and do it as a plotting one and ask them to plot it, they could get these ones, but they wouldn't get full marks unless they remember to include these asymptotes as shown with a dotted line. So yes, that's another thing to show them. We're supposed to write the equations of the asymptotes. So this is the line x equals 0, this is the line y equals 0, and this is the line x equals 0. I don't think they would lose marks for that. I think provided they'd shown the dotted lines in the right place, that would be sufficient. But it's always good to write where they are. It's also useful to write where they are, because then when they get translated, it's useful to know where to move them. So translating does just the same as it does in every other thing. So minus 1 means it's going to move to the left by 1, and minus 2 there means it's going to move down by 2. Now, in fact, what that does is it changes the bit with the x to whatever the opposite of that is, so that changes to x plus 1. And on the outside, we take off the 2. So that's our new graph, new equation for the graph. Now, the most useful thing is to think about what happens to the asymptotes. The asymptotes were originally at 0, 0. They will now be at minus 1, minus 2. So the most useful thing is to draw the asymptotes in first. Move to minus 1 and to minus 2. Then it's often easier to do that first, and then you can draw in the shape of the two bits. So like before with the cubic graph, we were looking at where are the bits that it crosses the axis and where are the stationary points, the turning points. Let's look at those and where those move. With graphs of 1 over x, the most useful thing is to think where are the asymptotes moving, and then just sketch in the other bits. You can always work out where these bits are, so where it's crossing here and here. So when x equals 0, we put x equals 0 into here, we're going to get 1 over 1 is 1, minus 2 gives us minus 1. So that's quite a useful one to do, the 0 of when x is 0, just to check where that crosses, because that should be shown correctly. Okay, so that's the graph of y equals 1 over x, and basically what we're saying is any function you have, you translate it by vector, you change the bit with the x to the opposite sign, and then you bung the bit with the y on the end. So, can you have a go at doing these three? So try and remember back to what we just did, sketching the x cubed and the 1 over x, and I've included another one that you might know or be able to figure out roughly what it looks like. And then I've been a bit mean, I haven't actually said what the translation is, I've given you the new equation. Let's see whether you can figure out what the translation is. In all of these, I'll say, in all of these, it's not going two ways. And I mean, it's not going up and down and left to right. It's only going to do one of those, just as a hint. So we'll do these and then take a break. Put your hand up. I think you've figured that out. Or given up figuring it out. Is that given up figuring it out?
Hello?
Hello? Have you figured it out?
Oh, you can hear me?
Yes, I can hear you.
Yeah, no, I've done. Sorry, I wasn't sure if you were speaking to me or not. I didn't quite hear.
Do you want to start with the first one? And actually, I don't know if it's, hang on, I think if I click through it, I haven't. Do you want to describe the first one that you've done?
Is this me, Wayne?
Yeah, I've just realised it's quite tricky.
Sorry, the audio's gone a bit. Yeah, so basically we drew the y is equal to x cubed one earlier.
Yeah.
And then I've just got it moving along to the right by 2, basically.
Yeah, good. Oops. Yeah, good. Good. And Robert, what about the next one?
Yeah, the standard 1 over x, and I've got it just simply going up by 2, so the new asymptote y equals 2.
Yeah. Oops. Yeah, this would show that. Right, what does this last graph look like? Oops. Yeah, Wayne?
Yeah, I kind of got it as like a from the origin, going off to the right, a kind of a low slope, sloping up. So when x is 9, y is 3, and x is 16, y is 4.
Yeah. And I've made it look flat there by mistake. It's a bit too flat, doesn't it? Shouldn't look quite that flat. It just kind of flattened out. Yeah, that's a bit better. Oh no, rubbish. Anyway, yeah, and then
moving to the left by 3. So starting at minus 3, 0.
Yeah, not like this. This is a bit rubbish, especially with my sloping axis.
Well, your slopes are better than mine, to be honest. But yeah.
Looks a bit like a rainbow. But yes, good. So that it goes over there. Excellent. Well, okay, let us take a break now. Be back at 10:02.
Yeah, that's fine.
Good.
10-2.
Okay. 10-2. I'll mute myself this time.
Okay.
You there, Robert?
Hi, yeah, I'm here.
How's it all going?
Yeah, I'm just not getting this essay stuff at all.
Yeah, I've kind of got to a stage where it's going to have to do. It's just, the more I look at it, it's like, what am I doing?
Yeah.
So,
I mean, I'm happy with the school and the
I
teaching
can't-
side, but it's just all this English theory and pedagogy, and I know it needs to be done, but
yeah, I know what you're saying.
we've got, sorry,
Sorry?
I say we've got one of our Troops to Teachers guys in second year, and he's taken the view that he's concentrating on the teaching and the QTS side, and the degree is almost secondary. It's just like a necessary evil, because once he's qualified, they're only going to be interested in how good he can teach and not how good his degree was.
All right, okay.
I can see his logic in it.
Yeah,
So I think
definitely. Well, it's already got to a stage. I mean, I spent, I'd say 3 days in the Christmas holidays just doing the assignment because I hadn't done anything on it, and I was trying not to do anything now. So basically, get it done in that period over Christmas. And I can see all these assignments for the future are going to be the same. I'm going to have to do them in the holiday periods because I just haven't got time.
No, I mean, I'm the same. If I'm honest, I have barely started it other than a rough plan. And I've put away Saturday and Sunday this week and next week to get it done. Hopefully writing it all this week and then next week polishing it up. But
Yeah.
as the timetable in class is increasing, you're getting more planning and more stuff in the schools to do.
Yeah, that's totally right. I mean, it sounds like you're teaching a lot more than me. I think you started a lot earlier, so.
Well,
I mean,
they've only actually given me two year 10 classes and a year 8 class to actually teach. And they're purposely keeping it low key at the moment. I've got 2 schools direct also in the maths department, and they're pushing way ahead. They're doing 5, 6, 7 classes. So they're not pushing us too hard. Which is nice, but yeah, it is. The workload is increasing with the essays, the assignments, and the teaching planning as well is getting heavier.
Yeah, exactly. Hello, Sarah.
Hello. I'm sorry, I'm just trying to wolf down a piece of Christmas cake. Desperately trying to find the Christmas cake.
I've just finished mine.
Oh.
I just finished mine.
We've still got a big wedge left, and it's so sweet. The icing is so sweet that I can't eat very much of it. And it's really difficult actually. I don't know about you, but we've still got bucket loads of really bad food for us. So we've got to kind of like empty the house of that before we can start being healthy again.
Yeah, sounds like a good excuse.
I know. I think the children have got enough chocolate to last into Easter. Definitely.
Oh no, the amount of chocolate in this house is just crazy.
That was about when we got rid of our Christmas nibbles. Was about the end of February. I think they were still eating them then.
Yeah, and I'm doing the same. I mean, I've been trying to force them. I've been like, please eat your chocolate Santas. And they're just like, no, can I have a Satsuma? Please eat the chocolate. Get the chocolate out of the house. But mine just, then they like a little bit every day. But really, I mean, my daughter has like a chocolate coin and 1 sweet. And that's it. Which is great. But just leaves us with bucket loads. I had to throw away their Easter eggs in the end because they went past their sell-by dates last year.
I've never done that before. That's a new one.
I know. I should have.
No, I don't know what they're teaching them at school because I said my daughter, she's only 6, but last night she said, "Well, do you want a bit of chocolate after dinner?" And she was like, oh no, I don't want any chocolate, I want to be healthy.
I know.
Like, 6 years old. I mean, I probably thought about that when I was about 36. But,
I know.
yeah.
Same with mine. I was a bit concerned actually because the other day, well, my daughter's refusing to wear her new winter coat because she thinks it makes her look fat, and she's 6. And I was like, what are you talking about? When she came home from school yesterday, and she was really upset because 2 of the girls in her class said she looked like a Yeti in it. I was just like, I don't know whether it's one of those ridiculous things. I don't know whether to contact their mothers and say, I'm sorry, but could you please talk to your children about not calling my daughter a Yeti? Obviously, I just said to my daughter, doesn't matter what other people say, you look great in your coat. Don't know where you're getting this thing about being fat from. Oh, yeah. But, yeah, seems to be there, you know, these teenage angst are there, age 6, aren't they? Oh,
Growing up too fast.
yeah. Yeah. Right. So at GCSE, they would only have to be able to reflect or translate the graph. And generally, they'd only just be looking at the shape of it and doing that. They wouldn't have to do the bits we've been doing with the equations. But at AS level, you also have to be able to stretch the function. So if we look at the graph of x squared, and then think about 4x squared, thinking about putting some points in, when we've got x squared, you just square 2, you get 4. But for 4x squared, you square the 2 and then multiply by 4, you're going to get 16. So as you can imagine, it's going to go up at a steeper level to the x squared graph. And what it's doing in terms of transformations is that all the y values are basically being multiplied by 4. Yeah, that's what it's saying. For every value of x, it's 4 times that. So what we say is it's a stretch of scale factor 4 because every single y value is being stretched by 4. It's being multiplied by 4. And we could say parallel to the x-axis, or you can say along the x-axis, y-axis, I believe, parallel to the y-axis. So it is basically taking your original x squared graph and just kind of stretching it vertically. There you go. So it's got the x squared graph, and it's as if it's been pulled up to make the 4x squared. So that is a stretch scale factor 4, and it was stretched this way, so in the y direction, along the y-axis. The only thing with the x squared graph is you could actually have looked at this slightly differently. So what we say is when we've got a number on the outside, so not with the x, then it's parallel to the y-axis. You know, like before when we sort of added the number on the end, that was the bit that was happening to the y-axis because it gets the whole graph and it moves it by that much. However, because of the nature of the x squared graph, I could actually have said that I was going to draw this graph, where if I multiplied that out, that would give me 4x squared, so it would be the same as this graph here. But in this case, I've actually got the number in with the x. So I'm squaring all of that bit. And if I've got the number in with the x, it's changing all the x coordinates. So you can think about it changing all the x coordinates instead of pulling up all the y coordinates. But of course, when it goes in with the x, it is the opposite to what we think, because we're kind of like, what is it that we have to undo in order to get back to our original x? So here, in order to get the value 1, I would need to multiply the 2 by 1/2. So what ends up happening is every single x value, it's not being multiplied by 2, as you might think by looking at this. You actually, to get back to the original value, you halve everything. So that's what's happened here. The other way of looking at this graph is that we could have taken the 1, 1 and we've halved the x value to get a half 1. So here they're taking a 0.24 has in fact now become 1, 4 because we've halved the x value. So you can either think of this graph as a stretch parallel to the y-axis of the scale factor 4, or a stretch in the x-axis. Now a stretch in the x-axis is nearly always a squash, really. Because it's the opposite, it nearly always ends up being a fraction, which means that it ends up squashing the other graph. So in this case, we still call it a stretch, even though it's a squash. It's just kind of a squishy stretch. So it's a stretch of scale factor 1/2 parallel to the x-axis. So that's a bit tricky, isn't it? Because we've just now done both types of stretches all in one because of the nature of an x-squared graph. It's not true of all graphs. For other graphs, you can still stretch them both ways, but it won't be mistaken for the other type. And were you asked to describe the transformation from this red graph to this blue graph, either one that you put would be correct. You could either say it was a stretch parallel to the y-axis of scale factor 4, or you could say that it's a stretch of scale factor 1/2 parallel to the x-axis. So that's just an oddity of the symmetry, basically, of an x-squared graph. So this is just going through all of what I've just said. In fact, the fact that it's the opposite, so we have to halve the x value to get back the same value of y. Quite a lot of things. Generally, though, whenever we have a number on the outside of the function, it's the scale factor of that value parallel to the y-axis. If it's inside the function, then the scale factor is 1 over that value, and it's parallel to the x-axis. For example, here we have them asking you to describe the transformation from y equals 1 over x to 3 over x. So 3 over x is the same as saying so it's 3 times 1 over x. So it's some number multiplied by the original function. So that's the first type, basically, that we looked at. That means that it will change all the y values and multiply them by 3. So it will be a stretch of scale factor 3 parallel to the y-axis. Let's show this. There we go. So here in red is our original graph. And it's tricky to see, but for example here, 1, 1, the value of 1 has been multiplied by 3 to now be 1, 3. And here is 2, 1/2. So 1/2 times 3 is 1 1/2. Okay, so that's how we can then show the two different graphs. So the asymptotes won't change in the stretch. They stay in exactly the same place. Just the graph is being stretched. And generally, they could get it stretched both ways, but that would just be really mean. So generally, they're just stretching it either in the y-axis, y-direction. Does that make sense? Do you think you will now be able to do this one, which again is a bit of a mean one? So that's a possibility. So describe, and it says describe A rather than the transformation of y. Wayne, do you have a question, or do you think you can do it?
I think I should be able to do it.
Okay, well have a go at doing it first, and then you both have a go at doing it first, and then.
I mean that's just stretching up. Well, I won't. Yeah, it's just stretching up the y-axis 9, surely.
Yeah. So that's definitely one of them. You could do, and try drawing yourselves little sketches as well. Okay, so I guess the other thing is then, so I guess I'll change the question to, what is the other transformation that it could be? Rather than a stretch parallel to the y-axis, how else could you describe it? You put your hand up and right, so Robert, what's the other transformation that it could be? If you're talking, you're on mute, so you get on mute.
There we go, having to put my mic on. I got stretch of scale factor third parallel to the x-axis.
Yeah, good. Yeah, so those are the two possibilities. So there you go. That's what it looks like. And yeah, it's always easier to think about what's happening in y, if that's possible, than just multiplying them. So it's much easier than the third one, but actually equivalent in this case. Good. Okay, so have a go at doing this one. This is just some generic function. I just want you to think about what these two stretches would look like. Okay, so have a go at doing this one. Wayne?
Yeah, I'm a bit stuck, I think.
Okay.
I was thinking that the first one was stretching the function bracket 2x. I was thinking that was stretching by a scale factor of 2 in the y-axis. But then once I did that and looked at the other one, I thought that was the same. So I've kind of not sure which one's which, to be honest.
Yeah, so this one on the outside is stretching it to the parallel to the y-axis because it's outside the function. So this is the function, whatever this function is that we've called f of x. So that's the one that stretches it twice. So this one, Robert, what does this one do?
I've got that one. The horizontal part is going along to the 4, and then it diagonals down to the 8. So I've got it stretching out to the right by double the length.
So almost.
But I'm not convinced about it.
No, so it is a stretch along the x-axis because it's inside the function. However, it does the opposite to what you think. So it actually halves. The scale factor is actually half. Yeah. So what ends up happening, if I click, here's the original one. F of 2x halves all the x values. So this, so say that this corner here becomes 1, 1, and this bit down here, 4, becomes 2. So that is f of 2x. So that is a stretch parallel to the x-axis, scale factor of half. And this one is the other one. The 2 on the outside, that does just multiply every y value by 2. So, I mean, this is very tricky, you know. It's thinking about a generic function that you don't know anything about apart from what you can see. And it's basically just trying to nudge you into using the fact that if there's a number on the outside of this function, it's in the y-axis and it stretches it by that scale factor. But if it's inside with the x, it goes along the x-axis and it's the opposite, it's half instead.
I actually wrote it down as a stretch of a half in the x-axis, but when I came to draw it, I didn't seem to believe myself and I extended it.
Yeah, so you'd have got
I just wasn't convinced of it.
You'd have got these marks, but then they'd have looked at your picture and gone, no.
Yeah, that's exactly what I did. I just multiplied it all by 2 instead of following my own theory of it being a half.
Yeah. But stretches are really tricky, and the students find them very tricky. Because there's quite a lot going on, you know, remembering each of these, and then rushing through in the exams, and they don't always, you know, think it all through or remember that it's the opposite and get confused between them. So yeah, this is something. So this is the thing that if you're finding it a bit tricky, you could put on your action plan as something to look at a bit more and stuff. But yeah, here are a few more using just this generic function notation. If we've got a negative sign, what do you think is happening to the graph? In fact, let's draw one. So whenever you've got a generic one, it can be really useful to just draw something and think about it. So I'm going to draw x cubed, for example. If I've got a negative sign, it's on the outside of the whole function. So it makes every y value negative. So that y value will be down there then.
So it's a reflection in the x-axis.
Yes. So reflections, again, really confuse the students because when we've been saying it's on the outside, so it was going to be happening in the y direction. Well, that's true because what's happening is you're dragging it down through the y direction. But the way that we describe that is in the x-axis, reflection in the x-axis. So it's a bit of a mean one. They've got to remember that a reflection in the axis does mean that all the y values are now negative, or the reverse, all the y values have changed. Whereas this one, f of minus x, what's going to happen to that? It doesn't help on this graph, does it? Because it looks basically the same. So if I just have this as my function, f of minus x means that all of the x values will now change sign. So that will reflect in the y-axis. So all the x values have changed, which means it's reflection in the y-axis. And what about this one here? What's happening here? A is just a number, a generic constant. Let me make that 3. So if it was minus 3 fx,
It's going to be a reflection in the x-axis.
Yep.
But something to do with the 3, obviously.
So what were we doing before where we multiplied the function by number?
So a reflection in the x-axis and moving down 3.
No, it's multiplying. So moving down would be if we were taking it away at the end.
Stretching by 3.
Yeah, but it's marvellous that you've said that because that is exactly the sort of thing that the kids, get confused by. Because it's got a minus 3 there, they think, oh, okay, so I'm taking away 3, I'm moving it down 3. But actually they've got a reflection and a stretch. And I also get them telling me that it is a negative stretch, which to them, because this is the thing with kids, a third is not the same as minus 3, and we know this, but to them, they're both things that kind of seem to make it smaller in their head. So I often get them thinking that that a minus 3 kind of shrinks it. But it's two separate things. There is no such thing as a negative stretch. It is a reflection and a stretch. So they find that quite tricky. Anything involving negatives, they're not sure. They're not sure if it's multiplying by something that's negative or if they're taking something away. That's the fundamental problem. They don't seem to really understand that this must be multiplied or something, that there's nothing else they're taking away from. So this is a summary of all possible transformations. So if you add a number on the end or take it away, then you move it up or move it down, and that's what it looks like in the brackets, and it's a translation. And if it's inside the function, then it's left or right, or the opposite of what you think. So when you're talking about translation, you need to have the word translation and a vector. If there's only ever, in GCSE, there's only ever one mark going. So unless they've got both bits, they don't get the marks. There aren't stretches at GCSE, but the same is true in AS level. It's only going to be a 1 or 2 mark question. So they have to have every bit of it in order to get those full marks. So they need to say stretch, the scale factor, and which way it is each time. And then, so there's 2 bits of information for those two, 3 bits for the stretch, and there's 2 bits for those. I saw someone, I forgot about the question, I meant to write it down. I saw someone, one of my students actually, who I teach at the university, did a starter on this, and it was a reminder, it was an acronym where, also the mnemonic really, where they had different letters and it told you how many there were of each thing. I can't remember what it was. But I think I will remember it and do it in the next session, because I think we're going to be doing, at the ISW, we're going to be doing some geometry, so we'll do some transformations of shapes, and we'll do some second. So in the transformations of shapes, I'll try and remember it, and then we'll do it. So at ASA level, they're expected to know all of these and apply them to absolutely any function they could possibly be given. Whereas at GCSE, they won't be given stretches. But let's just look at trigonometric graphs. This is sine graph, because sine soars upwards to 90, or pi over 2 if you're in radians, down to pi, down to 3 pi over 2, up to 2 pi. So this is y equals sine x. If we want 2 sine x, again we're just going to stretch it up to 2 and down to minus 2. And a half, we just half the scale factor, and still parallel to the y-axis. So there's all of those. Those are all stretches parallel to the y-axis. If we've got it in here, it starts to get a bit tricky, doesn't it? Because sine of a half x is in with the x, so it's the opposite to what we think. So it's actually a scale factor of 2. So it stretches it along the x-axis. So every x value is twice what it was. So where here we had 91, now we need to have 180 to get 1. There we go, at 180 we have 1. And at 180 it was 0, and now at 360 it's 0. So for sine a half x, you're only going to get half a wave in the 360 degrees. And we call that the period. No, we don't. It's just the number of waves that there are within the period. Oh yeah, wavelength. We call that the wavelength. I was thinking that. So generally, this is one wavelength. When it goes all the way up and all the way down, that is one full wave. And on a general sine graph, there's one wave takes 360 degrees. When you've got some sort of function with it in with the x, whatever that number is here, that is now the new wavelength. So here you can see you only have a half of a wave in 360 degrees. So the new wavelength is a half. The period, on the other hand, the period is the length of time, or length of time is not really time with this, is it? It's the length that it takes to do one full wave. So on a regular sine graph, the period is 360 degrees, or 2 pi. That is the time it takes to travel through one wave. Whereas you can see from the sine half x, you'd need to go another 360 degrees to complete a full wave. So if you were ever asked to calculate the period, it is in fact 360 degrees, or 2 pi, depending on whether you're doing in degrees or radians, divided by the wavelength. So normally that's just 1, but in this case it's a half. for this one. So the period is going to be 700. Okay. And equally, now we've got sine 2x. So the 2 tells me that in the 360 degrees, I'm going to get 2 waves in that space. And so the period will be 360 divided by 2, which is 180. But in terms of the transformation, that is a stretch, scale factor a half, parallel to the x-axis. Annoyingly, on the slides, I can see this, but I don't know why on the slideshow I thought. Bit of a weird glitch. Just the same as before, you add 1, it moves the whole curve up. Oh no, it's just go completely unfair. If you add 90, remember, oh, hang on, I think it moves curve to the right. But actually, technically, that moves the curve to the left by 90. So that is incorrect. Annoyingly, we've not seen which one's the original one. Well, it's got to be this one. The orange one, the red one, is the original one. We've moved it to the left by 90. Must change that. That's actually left. Because it does the opposite when it's inside. Oh, that's good. So here's the one that moves it up, the blue one, and then it's moving left. That might be it. I got there quite soon, haven't I? 11:30, okay. Half an hour early. I think you can take that time. So don't worry about the trig self-study, obviously just focus on the assignment for now. But I have uploaded a trig self-study. And in fact I've uploaded, they were split because how the trig webinars, you had one before Christmas and you had one now. So I split the self-studies into 2 as well. And because of the dates, they end up both being after both webinars. So you can do those whenever you get round to them. Because there's one in January, supposedly next week, and there's one on the 6th of February. But they're both uploaded currently onto the Student Central. And obviously, at the moment, just focus on getting your assignments in for Monday after next. And then you can do the trig stuff. And I will see you in February after half term. I'm going to be seeing you on the Monday afternoon. I'm hoping to do a problem solving session. And you're going to be with cohort 4. Now cohort 4 unfortunately is down to 1 person now, so it'll just be with you. And then I'm not sure which day I see you and which day I see him actually, but I'll either see you then on the Tuesday or the Wednesday for your subject order development. So yes, we're going to be doing...
Sorry, Sarah, sorry you're a bit muffled there, sorry. So we'll see you twice in that week, is that right?
Yes, I see you on the Monday afternoon.
See you twice in that week?
And then I can't remember, in fact let me have a look, I can't remember whether it's on the Tuesday or the Wednesday that I see you. And the reason I can't remember is because I realise I've had no information at all about it. I'm just I'm vaguely searching around and thinking, no, actually, I have no idea. Don't think I've had an email.
So we get a full day and a half with you, do we?
Yeah.
Okay, good.
Yeah, so that was the idea, was that they've reduced the number of webinars so that you can have more face-to-face time instead. And originally I planned to do, because it was with you from cohort 4, I had planned to do decision maths, but they've cut decision maths now from A-level, So it is only available to further mathematicians, sadly. So I thought I would do a more generic problem solving sort of session, which may have a bit of decisioning, but just something a bit more generic in mathsy. So I haven't written it yet. So we will see what it becomes. But yeah, so you'll have one session on the Monday afternoon with you, and then I see you either all day Tuesday or all day Wednesday, depending on which one is your day. But yes, if you could bring compass and protractors for our day altogether, because we're going to be doing circle theorems and loci, and just, I think we're doing geometry, rather than guessing. I think we're doing geometry, yeah, so problem solving on the Monday, and then geometry, which is transformations of shapes, loci, and circle theorems, and then we're going to be doing probability in the afternoon. And then when I see you in June, we'll be doing stats and some GCSE exam questions. Oh yes, and so I've moved that topic to year 2 because this problem solving one is a bit generic, and I didn't do that before. Before I did like a GCSE statistics one, but I'll move that to next year, as Hugh has already done that one. But we'll see how it goes. Apparently for next year they are recruiting a cohort 5, so it will continue to continue. But it's only for certain subjects, but maths is one of them.
How many people started on cohort 3 then?
4 of them.
4, and there's only 1?
Yes. So 2 of them, well, one, Sam is at Robert's school, and she's decided to completely give it up and do her own thing, which she's really enjoying. The other two guys have taken a break from the course, so they're supposed to be coming back to it. So Mark will probably rejoin us next year. He'll join you guys, and so there'll be 3 of you doing next year. But Matt was supposed to join us now. Oh God, I didn't send him any information. But I don't think it's because I haven't sent him any information that he's not joined. I think I haven't had a confirmation that he is definitely coming back. So he gave up due to illness, or paused due to illness. So I guess he was hoping to come back and join you guys about now. But then when we found this out, I did sort of say, well, that's a bit unfortunate because he's kind of got to do an assignment in a week. But maybe he's decided that he'll come back and do cohort 5, and I don't know. But I think we'll definitely get Mark back next year. He'll join you guys for your final year. So yes, my cohort 3 is very quiet. I think Hugh and I will probably get through the webinars incredibly quickly. So yeah, people will say that. But yes, so let me just go on Student Central. Have you looked? I haven't looked yet. Have they set up a Turnitin space for you to turn it in? Let me just check if that's happened. I used to set up my own Turnitins and then discovered that they did it, Brighton were doing it too, and then it got confusing because there were 2 places and it was confusing.
I think they set it up the week before Christmas.
Okay.
But that just scared me into
yeah.
completely ignoring it until after Christmas.
Yeah, there we go. So it's just under assessment, and you just upload it there. The top one. So yeah, so good. That's there.
Just a
yeah.
Just a quick question, actually, Sarah. Once you show me that, I think Liz posted something on Facebook to say if you wanted to attach evidence, do it at the end of your
Assignment.
document, basically.
Mm-hmm.
Yeah.
Yeah.
Which is fine, but I wasn't sure how to actually get it on there, right? Apart from printing the document off, scanning it all together as a PDF, and then uploading it, which seemed a bit...
No, you see, this is the thing. What used to happen, what the other guys did, was they just emailed it to me. And that was the problem. They said that it then wasn't through official routes. So, because they were audited last year, and then I got these emails from whoever it was, the secretary who was doing it, saying, did you have this, 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 and this? I said, oh yeah, it was all emailed to me. And they were like, we've got no paper trail on Student Central. So that was the problem. They had no paper trail on it. I wonder if you can upload more than one. No. Can you not upload more than one?
No, I think it just over...
There you go. Multiple file upload.
I don't know, I'll have a look. I thought it just overwrit the first one, but maybe you can multiple upload. I hadn't even looked at that.
If I remember from the last assignment we did in December, I think we uploaded some to a folder on PebblePad.
Yes,
so
that's
that
right. That's what we did.
they were the appendices or something there, and you uploaded the actual assessment to Turnitin. But any additional stuff was available on Student Central somewhere. Up on
Yeah, we
PebblePad.
uploaded the resource into PebblePad, didn't we?
Yeah, that was it.
Into a separate folder. Yeah.
Okay, well, if that's what's supposed to happen, do that. But could you also email me any extras? Because that saves me hunting out my PebblePad login. And
Okay. Yeah.
and then I'm just more likely to check that. Well, basically, I will definitely check that. As I kind of do that once a week, check my Brighton one. Whereas I think I've finished PebblePad once, I'm afraid. So when you do, yeah, when you upload your Turnitin, well, let me stop recording.